Next up, we're going to talk about the process of science. Science is actually very, very organized in a highly regulated sort of procedure. It's how we go about learning about the world around us, and this happens in a very organized way. A method that's known as the scientific method. This is going to include various steps like observation, hypothesis, predictions and experiments, data collection with statistical analysis, finally a conclusion. This may seem like a lot of information, but actually it's very sort of common sense, if you want to call it. Very, very sort of common sense way of proceeding to figure out stuff about the world. Very, very scientific terminology. But we're going to start off by looking at observation. Observation is just scientists using their senses to gather information about a phenomenon or a natural event. It's like going outside and being like, the sky's blue. Cool. And that's it. Like, that's observation. You simply are observing using your senses. Or you go, ooh, it smells like fresh cut grass out here. However, it's not enough to just observe the world about us. We need to, we're never going to learn through just observation. We then need to explore. We need to be curious about those observations. It's not enough to go, sky's blue. Cool. We need to go, why is the sky blue? What does it mean that the sky is blue? So the way that scientists do this is by forming what is known as a hypothesis. A hypothesis is a tentative explanation for what was observed. So for example, was the discovery of antibiotic penicillin. The scientists who discovered that penicillin could be produced or is an antibiotic found that he left some petri dishes out, and he found that in an area there was a certain fungus that was starting to grow inside of his petri dish that was containing a very specific colony of bacteria. And what he found is that in a ring around this fungus, there was no bacterial colonies. And he went, there's no bacteria around this fungus. That's a little bit bizarre. Well, let's think about it. Maybe there is something in the fungus that is producing a chemical that is preventing the bacteria from being formed. That was a hypothesis. So it's developed through inductive reasoning, and it has to be testable. So your hypothesis has to be like, okay, I think that the fungus is producing a chemical that is preventing bacteria colonies from forming. So once you have a hypothesis, then you develop a prediction. A prediction is like, okay, this is now how I'm going to test my hypothesis. So predictions and experimentation. An experiment is just a series of procedures designed to test a hypothesis. It utilizes deductive reasoning to make a prediction or an expected outcome. The manner in which scientists conduct an experiment is what's called experimental design. A good experimental design ensures that the scientist is examining the contribution of a specific factor called the experimental or the independent variable to the observation. So the experimental variable is the experimental variable that is being tested. So in this case, my prediction would be, okay, if I intentionally grow fungus in the presence of bacteria, the bacteria will not grow. So I'm going to smear a plate full of this fungus, and I'm going to streak it along with this bacteria as well. And my prediction is that in the presence of this fungus, bacteria will not grow. So my experimental variable is going to be the variable that's being tested, and that would be the growth of bacteria. So in the process of using experiments, you're going to need what is known as a test group. The test group is going to be exposed to the experimental variable. A control group is also going to need to go through that process. The control group goes through all the same aspects of the experiment, but is not exposed to the experimental variable. If the control and the test group show the same results, the hypothesis is not going to be supported. If your hypothesis is not supported, you go back to the drawing board. You reject your hypothesis and you try again. You're going to keep doing this, and each time you do this, you're going to be collecting data. Data is often going to be demonstrated through tables and graphs. There's just formats for that data. Data is then going to be analyzed using statistics. And we can use a whole lot of things. We can measure variation, so standard error. How far off is the average of the data? Statistical significance, probability values. There's a lot of stats that go into data collection and analysis, so we're not going to get into any of that. We're not going to be analyzing we're not going to do any statistical analysis in this class. We're just going to be doing mostly observational data collection. Once you've collected your data, you can then draw a conclusion. The conclusion is going to be the data that are interpreted to determine whether or not the hypothesis is supported. If the prediction happens, the hypothesis is supported. If the prediction does not happen, the hypothesis is rejected. Those findings are then reported in scientific journals. Peers review those findings. Other scientists then attempt to duplicate or dismiss the published findings. So if other scientists in other conditions can produce the same results, then your hypothesis is going to be supported. If they are unable to support your hypothesis, they may dismiss your data. Scientific theory is concepts joined together by two or more well-supported and related hypotheses. And these are going to be supported by a broad range of observations, experiments, and data. Something cannot become scientific principle or scientific law until it is a very widely accepted set of theories. Now, I know there's a lot of words, but we're going to break this all down. So just for an example, we're going to say we're going to be testing out a new antibiotic. And we want to see if this particular antibiotic is going to be more effective, this new antibiotic that we came out with. We want to see if it's going to be more effective than the leading brand of antibiotic that's out there. So what we're going to do is first state a hypothesis. And our hypothesis needs to be simple and clear and concise. A good hypothesis is like a true or false statement. It's got a yes or no answer. It's binary. A good hypothesis is very clear, very observable, and very easy to either support or reject. So our hypothesis in this case, if we want to compare the latest and greatest new drug out there to, whatever is the current leading brand, we're going to start off by stating antibiotic B is a better treatment for ulcers than antibiotic A. Very simple. That's a very cut and dry statement. It should be either true or false. Antibiotic B is a better treatment for ulcers than antibiotic A. So how are we going to do this? We're going to start off by getting a test group, and we're going to need to break our individuals into 3 different groups for testing. So we need to perform this experiment because we want to know not only does antibiotic B work, but we need to know that it works better than antibiotic A. So we're going to break our individuals or our test group into 3 categories. First is going to be our control group. Our control group is going to receive a placebo. What we find a lot of times with medicine is that if individuals think they are being treated, they're going to behave differently and they're going to potentially respond to treatment better just because they think they're getting the treatment. Fantastic example of this. When I was younger, I used to have really bad headaches. So my mom used to give me Tylenol for my really bad headaches. And I'd be like, wow, I got my Tylenol and I already feel so much better. And she'd be like, no, it's not even going to kick in. It's not going to reach your digestive system or be absorbed by your small intestine for at least another 30 minutes. There's no way you actually feel better now. But I did. The headache literally went away as soon as I was given something to treat it because the body has an amazing ability to respond and heal. Now, of course, my brain knows better. It knows that it takes 30 minutes. And so now I don't start feeling better. If I start to take, Tylenol or a pain reliever of some kind, it doesn't work until it's prescribed to work because my brain cannot be tricked anymore into thinking that it is healed. Anyway, that's neither here nor there. That's just the placebo. So the control group is going to receive the placebo. They receive no drug at all, but they think they are receiving the drug. So that way we can see what sort of psychological effects may have on the healing process. So group 1 receives a placebo. Group 2, or the control group receives the placebo. Test group 1 is going to receive antibiotic A. Test group 2 is going to receive antibiotic B, and we're going to see how they compare. So the next step is we're going to collect that data. For this case, if we're examining the presence of ulcers, we're going to use endoscopy. It's a procedure that allows doctors to examine the linings of the throat, stomach, and upper small intestine to check for ulcers. This is going to be performed on all subjects, even the control group, because we need to know how they compare to test group A and B. Finally, we're going to collect data. We're going to use statistics to determine the effectiveness of those various treatments, and then on the basis of that data, the investigators can conclude about their hypothesis, whether it's been supported or not. And what we see here, and I'm sorry, it's very small. Let me see if I can zoom up on that. No, it's not zooming. That's all right. But if you look down here, you can see that in the control group, we see very few of the individuals in the control group were treated. Now, some did see positive results with the placebo, but not everybody. And there was significantly more individuals that were treated with antibiotic A. But there was also then a huge improvement between 60% of individuals saw a reduction in ulcers, 80% of individuals saw a reduction in ulcers in test group 2. So we can see there was a significant difference between antibiotic A and B. Thus, we can conclude that antibiotic B is going to be a better treatment for ulcers than antibiotic A. So that's the scientific method. You're going to be performing a lab this week that's going to help walk you through the scientific method and just help explain things in a little bit greater detail. A very important step in a lot of the labs that we will be performing this semester is going to be the prediction step. So you're going to observe a particular phenomenon, and then you're going to predict how you think that might turn out. And then you're going to look at whether or not the data supports your prediction. Predictions are not right or wrong. It's not, you will not be docked any points for having a prediction that is not supported by your data. This is just a way for you to engage in the material and to see if the results you got were the results you expected to get. Or if something completely different happened, if you need to go back to the drawing board and come up with a new hypothesis. So that's going to be the scientific method, or the process of science.